Hello guys, in this video, I'm going to be going over how to write the proof for this statement right here. So we want to use the contrapositive to write this proof, and that is called the method of proof by contraposition. So in order to first start writing this proof, we have to put this statement into the form for all x in some domain. If P of x, then Q of x. So usually for this step, I usually just think, okay, I have to write this sentence in if-then form. I don't always write the for all x in some domain. I don't always write that, but I do write the statement in if-then form. So if this, then that. So the negative of any irrational number is irrational. We're only dealing with one variable since it just says any irrational number. So I could introduce that by saying if n is an irrational number, then the negative of n, so then negative n is also irrational. So now, what you want to do is you want to take the contrapositive of this sentence right here. So remember that P implies Q is logically equivalent to the negation of Q implies the negation of P. So this right here is P. This right here is Q. And in order to take the contrapositive of the sentence, we say if and then the negation of Q, which is negative n is not irrational, aka negative n is rational because the opposite of irrational is rational. So if negative n is rational, then n is not an irrational number, aka n is a rational number. Okay, so I'm going to write contrapositive right here. So now what you want to do next is you want to prove the contrapositive by a direct proof. So this right here is the contrapositive, and you want to prove the contrapositive by a direct proof. So you say, suppose, or assume. So suppose, and then you write the if part of the if-then sentence. So suppose negative n is a rational number. I wrote a rational number instead of just saying negative n is rational, same thing. So now we want to define the technical terms. So rational is a technical term. So the definition of rational says, a number is rational when there exists integers a and b such that the number can be represented as a quotient of two integers and the denominator is not 0. So I could say, by definition of rational, negative n equals a over b, where a and b are elements of the set of integers. Notice that we want to prove that n is a rational number. So we just showed what it means for negative n to be a rational number, but we're going to reuse this definition to show that n is a rational number. So since the definition of rational means a number can be represented as a quotient of two integers, that means n can be represented as a quotient of two integers. So keep that in mind as you're writing the proof. So let's introduce n. Well, how can we do that? Well, we know that negative n equals a over b. So by doing algebra, if we multiply both sides by -1, if we multiply both sides by -1, then negative n equals AB times -1 times -1 equals, I'm not going to write like this because it's a bit confusing, so times -1 times -1, that equals -a over b. So we know that -a and b are elements of the set of integers because integers are closed under multiplication. What does this mean? What does this mean? It means if I multiply integers together, the product is an integer. So here, -1 times a creates an integer because -1 is an integer and a is an integer. So -1 times a, whatever that is an integer. Also keep in mind that -1 times -n is n. So we just showed that n equals -a over b, and n equals a quotient of two integers. So now we can say, let r equal -a. This means n equals r over b, where r and b are elements of the set of integers. So now we can clearly see that the format of n is the same format as -n, and that means this right here is the definition of rational, which is the definition of rational. Thus, we just showed that n is a rational number, right? N is a rational number. But instead of writing the then part of the if-then sentence like we usually do for direct proofs, we're going to write the entire contrapositive. So we're going to say, thus, if -n is rational, then n is a rational number. Therefore, remember that if we prove the contrapositive, then we prove the conditional. So we just proved the contrapositive, so now we can say, therefore, by the contrapositive, because of the contrapositive, the conditional is true. So we could write the conditional, or we could write the original sentence we wrote right here. So we could say, therefore, by the contrapositive, the negative of any irrational number is irrational. And that's how we prove this statement right here. And we could put a little square symbol to indicate that this proof is done.